Good morning, everyone. My name is Usman Diao from Senegal. I am a postdoc fellow with MAP, Malaria Adults Project, based in Ifakara Health Institute in Tanzania. Today, I would like to talk to you about fine-scale spatial risk map of incidents in Senegal. In 2023, many countries in Africa has started to update their national strategic plan in order to better fight against malaria. One part of this plan, the program would like to understand how their malaria data are distributed in space and in time. And in elimination settings such as Senegal, the program do not run surveys because they consider that they have few cases, and also surveys need more time and are expensive. They only relied on data such as incidence and prevalence. And that's why this work is requested for MAP in order to explore the fine scale heterogeneity of malaria transmission in Senegal to support decision making. So clinical case count data from health facility are very important and fruitful for mapping disease burden, especially in elimination settings. But working with this kind of data presents many challenges. One challenge is the missing information on health facility catchment, because we do not know well the population around some health facility that go to seek treatment in this health facility. And also the denominator of this population is not well known. For the second challenge is we have uncertainties regarding treatment seeking, because there is a big difference between seeking treatment in rural and urban. Also, we have some asymptomatic cases that are not well known because they do not go to health facility to seek treatment. And for challenge 3, we have not all the set of the health facility, because some private health facility do not regularly report data. And that's why their locations are not known. And also the population that they cover for seeking treatment is not well known. For the data, we use the routine data from 2020 to 2023. For all cases and for all age and from 1,000 to 151 health facility, and 52.2% of these health facility are zero-located. And here in this 3 map, we can see how these cases are distributed and how the malaria cases are low or high in Senegal. But also we have health facility in all districts in Senegal, and that's why we consider that even the set of data is not very high, but it is very representative to give us reliable prediction. The model that we use here is a classical geostatistical model, where we consider a negative binomial distribution because we have account data. And we also add a Gaussian process function for its space, random effect. And we also consider covariates that we obtain from satellite image. And what we do here is we consider observation data. For input, we run our model through a negative distribution, taking into account these different covariates in order to obtain a pixel level prediction map. For covariates, we consider these 16 covariates that are well known to influence the malaria transmission. For example, we have the accessibility to cities, aridity index, temperature suitability for the Plasmodium falciparum, so the day or night temperature. For developing this model, we have listed some challenges, and the biggest is to determine the catchment population associated with the cases estimated, because evidence shows that people do not always attend the facility that is nearest. And here we can observe in this picture how people are seeking treatment around different health facility, because there is not an automatic choice of the health facility. What is catchment model? Catchment model assigns a probability CJI that the people in each household J will seek treatment at health facility I. And for example, here we can see, for example, a household number 4 can seek treatment in the health facility number 1 or 2 or 3, because there is a preference for householders to seek treatment depending on some reason. One of the reasons for preference to seeking treatment in the health facility is the relative cost of care or the reputation of some health facility, but also some commodities presented by this health facility. And to take into account this component, we consider this model where the proportion of seeking treatment is calculated by attractiveness parameter and divided by the square of the travel time. And here we consider the travel time instead of the distance, because we consider that this parameter is better to use, because, for example, you can have a household near to a health facility, but to go in this health facility, you can encounter some difficulties, such as mountain or river. And for the travel time is better to use to calculate this parameter. And we fix a threshold for this travel time. We consider only the values less than 180 minutes, and over these values, this parameter is considered as 0. And for the proportion of seeking treatment, we consider the values for seeking treatment in one health facility over the sum of all health facilities. To fit the information with this relative attractiveness of health facility, we also consider data such as malaria and no malaria data, because, for example, in the health facility number 2, we can measure the attractiveness of this health facility by showing the data from all the person that go to seek treatment after having a simple fever. And we add this component in our classical geostatistical models that we present before. And the expected cases at its health facility is often by summing the incidence of all pixels weighted by the Cashman model. And generally, we want to know the possibilities that not everyone with a fever will seek treatment. And to calculate this proportion, we use this logistic function, which depend on the travel time between pixel place to the nearest health facility. And the parameter alpha, beta, and sigma are fitted taken based on some value fixed by fixed depending on the possible treatment seeking proportion. And we add also this component in our model, and here we can obtain the expected incidence by considering the Cashman model times the theoretical incidence times the population density times the treatment seeking population. As a result, we obtain this map by pixel level, and we can see how the theoretical values are distributed in around the country. We aggregate this pixel level data by district level, and we make a comparison between the observed data in the top and the predicted incidence in the bottom. For example, we can see there is a difference in 2021 between the observed data and the predicted data. And we consider that this can be explained by the addition of the Cashman model in the classical geostatistical model. And also we have a difference in 2022. For that, we consider that this is caused by the treatment seeking component adding in our model in this region. So these different maps are used, for example, in the annual report of the NMCP of Senegal. And also they are used to make in place dashboard. For example, we have this image from a dashboard and the development by IDM. So this model presents some limitation. For example, related to the data, as we said in the past, we have not a total set of health facility. And also we consider stationary population density during our period of study from 2020 to 2022. And also in the model framework, we consider some assumptions such as we use a stationary Gaussian field, also a linear predictor for our covariates, and we consider a simple gravity model. So to be clear, our model aims to predict rather than to explain, which implies a compromise between prediction performance and interpretability. To conclude, in this study, we use a classical geostatistical model where we have added customer population and treatment seeking component. And with this model, we have produced a series of maps for these 3 years. And we have presented this map to the National Malaria Control Program of Senegal. We also, with our covariates, we have developed some work related to the influence of the dominant covariates by pixel or by admin level. We are developing study about the monthly risk map. So this result of the map are used for these different companies in order to help for decision making. And I would like to thank all this structure, and this work is supported by Bill and Melinda Gates Foundation. And thank you for your attention.
Excellent. Thank you very much, Usman. I think we have time for 1 or 2 questions for this one. Jaylee?
Donc, merci pour la belle présentation. I wanted to ask about the facilities that don't have coordinates because it was a substantial fraction. And I was curious what kind of facilities these were, if they're reporting malaria cases, if they are the private sector, if there is some geographical clustering of these facilities. I was just curious.
Okay, thank you for this question. So most of time, the missing health facility are from the private sector, because for Senegal, the health facility are the possibility to report data to the DSS2 platform. And sometimes if they are not happy for the government, they keep the data, and for that we will not have their information in the platform. That's why this GPS coordinate of health facility are not known by us. Yeah.
Caitlin?
Thank you very much. So I didn't quite capture, so is the assumption that the attractiveness of the different facilities is fixed over time?
Okay.
Year to year.
Yeah, I think it can depend on our units that we consider, because here for the map we are mapping 4 years, but if you are mapping for months, you can consider parameters that can change by months. Yeah.
Okay, great. Yeah, let's talk about it afterwards.
Yeah. Thanks very much, Usman. I think we'll hand over to our next speaker now. That's great. And we have a little change to talking about vectors instead of the parasite with Eric. Thank you.
So, good morning, IBMers. So, I want to welcome you to my presentation this morning on modeling spatial-temporal dynamics of malaria vector niche overlaps in Africa. So this is an ongoing project we are doing at ISIPE called the Vector Atlas, funded by the Melinda and Bill Gates Foundation. Thank you. So as the previous speakers have said, when it comes to talking about the same thing, introductions, mostly it's common knowledge that we are having a lot of burden in Africa, and we are having quite the death surges and also the malaria cases increasing. And of course, we have quite a number of populations at risk, may it be infants, children, and also some countries are having a lot of, cases of malaria deaths worldwide. So this is mostly knowledge among the malaria community in Africa. So where we are coming in as Vector Atlas, we are abstracting data on primary and secondary vectors. Reason being, to control the vector, of course, you have to know where is that vector, which type of vector, because they normally have different ways of transmissions. I mean their responsiveness in terms of transmitting the vector. So we are abstracting data on primary vectors and secondary vectors within the African continent. And one important thing to note is when we always look at the vectors, we have the primary and the secondary vectors, of course, primary accounting for 95% of the transmissions and secondary ones accounting for 5%. But things are changing. Reason being, you find that as we keep on controlling the primary vectors, the secondary vector populations keeps on ballooning, and therefore residual transmissions always keep on propelling. And that's why we end up having some areas recording transmissions throughout the year, while others not throughout the year. And also in terms of control, because in our project, we're also looking at controlling the vectors using ITNs, IRS. So one question we are asking ourselves is, when we target, we use those control measures, you find that we are suppressing the primary vectors, but the secondary vectors still remain flourishing. And again, because of climate change and a lot of changes, we are having also the secondary vectors transitioning to primary vectors. For instance, Anopheles arampiensis, which was a secondary vector in 70s, now it is a primary vector. So as we look into the future, the question is, what about the secondary vectors, which when we control, mostly they are resting outdoors and they are biting outdoors, so we don't mostly target them. What is the case, for them in the future as we reflect about the control of the vectors? So in our case, we wanted to look at where we are having these primary and secondary vectors sharing the same habitants, because with such places, we are having a likelihood of intensified, sustained, and prolonged residual transmissions. And again, as I've talked of these vectors, as we look at it, for instance, the Anopheles stephensi, we have looked at it, it came to Africa through Djibouti in 2012. But right now, we are talking of it being in Nigeria. 2024, we are having some cases being confirmed in Ghana. So that means that the vectors may be here, but after some time, it will be found somewhere else. So as we model, we want to account for that. And also, another thing is what we aim to have is to try to identify these niche overlaps so that this work we are doing, when it is blended with like the distribution of the plasmodium and also the breeding sites, we can have a more concrete information to policymakers on where do they need to target and what kind of interventions they need to target based on the vectors which are there. So just about the methodology, we have mostly targeted the African continent, because basically our project focuses on the vectors occurrences in the entire Africa. And coming to modeling, we have over 50 secondary vectors in Africa. But for the case, we are still collecting more and more data with partners and also with publications. And in this model, we just focused on Anopheles, Gambic complex, and the Phrestus group. In the secondary vectors, we had the Pharensis and Anopheles costani. But we are also, sorry for that, we are also intending to extend this to more vectors as we keep on collecting more data. So these we are modeling it informed by the environmental variables which we have used. Of course, we even tested them to see whether there is any correlations between them and the occurrence of the vector species we have. And the time scope, of course, it was from 1985 to 2021. So looking at the methodology we have used, we reflected so much. As we collect the data, we have looked of over 15,000 papers published by various people in the African context of how these vectors are behaving. We note that some studies just which collect the occurrence over time, they try to say that we are having vectors at a point and with the time we have them in the neighborhood. So that ballooning context. Then we also reflected about it in terms of also the Anopheles stephensi. Why is it transitioning also from Djibouti all the way to Western Africa over time? Yet we couldn't say in 1912, in 2012 when it arrived in Djibouti, it is shifted directly to Western Africa, but over time it has evolved. So with that, we also looked at various literature. What is it telling us about the vector? Is it static, or sometimes it also moves to the neighborhoods? And one of the information we got is that yes, it can be static over time or throughout its life, but also sometimes it can also move in order to get the mates, if feeding also, or looking for being propagated by transport and wind. So in terms of modeling, we decided now to go for the cellular automata approach, which will enable us to look at how these vectors are transitioning from where they are over time based on the environmental conditions in the neighborhood, and also restricting the far they can go based on literature, because most of the studies on capture-recapture method are arguing that yes, it can even be propelled up to 50 kilometers based on various factors such as wind, or it can still stay somewhere, but majority were ranging among 5 to 10 kilometers. So using the cellular automata approach, and using the cellular automata approach, which normally works on that concept of you identify a place where you have located the vector itself, then you look at the neighborhoods of that place. Are the conditions there in terms of the predictor variables you are using, are they allowing the vector to shift there over time? So that propagation, we took it on monthly basis, given the lifespan of adult mosquito vectors, but restricting ourselves to grids of 5 kilometers across the African continent. Of course, we can go to lower resolutions, but our data collection is based on the assumption of 5 kilometers, because some studies, while publishing the data, they are giving us coordinates, but we have to give us our levels of uncertainty. So we looked at the state of the cell. Do we have the vector there? Then in the next time step, we look at the neighborhoods, how probable it is for the vector to move over there. Then basically, this is now the implementation of the methodology. Of course, cellular automata depends on the transition rules crafted between the occurrence of the vector and the predictor variables. So we deduce the rules, which now tells us the association. And then after that, creating the rules, we gridded the map of Africa. And then we rolled out based on our occurrences, where we have located it initially, and over time, how are they spreading? But one thing we appreciate is that there is a challenge and gaps in terms of the data collected before 2000. It's really scanty. So in order to make our model more stable, we kept on updating the inputs with the new collections we have had. But to validate the model, we put aside the data from 2018 to 2021, so that after we predict the dynamics there, we can look at how are they coinciding with where we have predicted the niche overlaps. So these are now the results. We had 1985 going at timely monthly time steps, but I just chose some of the years in terms of December to just show the evolution over time. So green colors and various colors just show where we have niche overlaps between a vector and another. Each vector, we have given it a key, like number one, it's the Anopheles gambic complex. Number two, the Phnestus. In this case, the two are the primary vectors, and 3 and 4 are the secondary vectors. But we appreciate in some cases, these primary vectors are also secondary vectors in some places. So it keeps on varying. So this is for the period 1985 to 2017. And then this is the validation output showing where we have overlaps between these vectors we are having. So just looking at this map and looking at the transmissions there, we see that where we are having quite a number of niche overlaps between primary and secondary vectors, we are still having sustained malaria transmissions based on the map obtained from the World Health Organization there. So why do we have this? It's in order to inform where we have the vectors. Can we also look at the maps of where we have the niche overlaps? Can we look at the maps of the plasmodium? We integrate them together and try to look at which areas do we now need to go and prioritize, because the vector occurrence itself won't mean malaria transmission is there, but we need the plasmodium there. So with that, just to conclude, so we appreciate that just by looking at these 4 vectors, we are having many residing together. And where we have them, as we look at the interventions we are using, we need to tailor them. For instance, we are having a study on plasmodium. I mean, we are having a study at ISIPE, which is looking at the microsporidia MB, which targets vectors which are indoors and also outdoors to try and reduce the transmissions. So when we look at Africa, still, because of the secondary vectors, we are having heightened risk and hotspots. So we need to look at that and not to omit the aspect of secondary vectors in what we are doing. Again, this approach using the dynamic spatial temporal approach, it also reminds us that as we model the vectors, we need always to account to where are they over time. We keep on building our models, appreciating vector is here or it is not here, because the conditions may be okay for vector to be there, but that vector has not been there. So we'll again predict that it is there, but it is not there, the vector itself. So ongoing, still we are working on this, because I said we will bring more vectors on board. We are creating a platform on the same, and also my colleagues are also working on the plasmodium predictions, which we need to integrate together and get a more conclusive maps which can inform the community, the malaria community, and also policymakers on rolling out the more targeted interventions. So with that, I want to conclude at that point. Then appreciate, of course, the Melinda and Bill Gates Foundation who are sponsoring that project and also sponsoring me to be here, and also the ISIPE donors who normally sponsors all the projects we work on over there. Thank you very much.
Great, thank you, Eric. We have time for a few questions, if there are any. Jaylene.
Thanks, Eric. That was really interesting, and I thought it was super fun, the combination of the cellular automata with the geospatial techniques. I've never seen that before, so thanks for that. I had a bit of a question on the occurrence data that feeds into the model, and as we know, entomological data is all over the place, and to what extent, absence of evidence is not evidence of absence. So not finding a secondary vector may mean that you did not look for it, you did not look thoroughly enough, or something like that. I'm just curious how you interpret lack of finding a species?
Actually, I'll say most of our focus it's on the occurrence, the presence only, because in coming up with our model, we look at a study after doing the test of the vectors which they trapped or collected there, have they identified that this is this vector, this is not. So we have just focused exactly on the presence only and informed by experiments which have been done by the studies, other than looking at the aspect of absence. Yeah.
Thank you for the great presentation. I was wondering, have you been including any information about human behavior in your model? For example, maybe there are places where people spend more time outdoors during the biting times of mosquitoes, which may influence the distribution of the species as well.
Actually, I want to say in the vector atlas, we are having 3 branches of the data we are collecting, one on the occurrence, another one on the bionomics, and another one on insecticide resistance. So for my case, I happen to be on occurrence and insecticide resistance. Then I have a colleague, Grace, I was seated with her, who is looking on the bionomics themselves, like that culture. People staying outdoors, of course, being beaten so much by the secondary vectors. So here I've informed my model on the environmental variables, but we are still collecting data on that. Where we identify the data, we look at the bionomics in terms of that paper as said what, then Grace is coming up with a model on the same. So integrating all these products will have a more conclusive, but we appreciate as a limitation, not so much as being shared on the bionomics of, the vector and also the culture of people, keto, they just say we have keto, but not so much deep into it. Yeah.
Yeah. Human behavior data is very difficult to
Exactly.
get. Yeah. Thank you very much.
Other questions? Eric, I have one quick question. So in your species overlap maps, there was more kind of overlap of primary and secondary vectors further east, and in Central Africa, it looked like there was still just the dominant primary vectors. It could be accounting for kind of the lack of occurrence data there, but do you suspect that it's also perhaps that the pressure from interventions has driven up the occurrence of the secondary vectors more in East Africa?
Actually, one thing I want to appreciate even drawing this way of cellular automata is that we really have so much data, sparsity of data in some countries. We don't want to say it is sparse, but you find that maybe it's not shared out. So as we look at context of DRC Congo, in fact, we had very limited data over there, but still it could confirm that we have the 2 primary vectors there. So I feel like, yes, the interventions could have accounted for that. And that's a rainy area so much in a way, but it's still subject to very much verification based on the interventions we have, because the data we are having, it's really reported in a poor way. And one thing the Malaria Atlas project did, it tried to identify, to estimate the interventions in terms of ITNs and IRS. But one thing with estimations, of course, there is always a level of uncertainty. So I don't want to be so conclusive about it. Yeah.
Makes sense. Thank you so much. So we'll thank Eric for his presentation.